Um, our learning goals here are to define an object, image, transformation, translation, vector. And we're going to describe a translation and determine if a shape has been translated. Just a little refresher on transformations. Okay, if we change the size, shape, orientation, position of a figure, that's called a transformation. And if we just do these, orientation or position, these are called rigid transformations because the shape's not actually changing what it is. Okay? Reflection, rotation, translation, and enlargements are all examples of transformations. We can describe these transformations mathematically using transformation geometry. In transformation geometry, figures are transformed in size, shape, orientation, position according to certain rules. The original figure is called the object. Okay, so this is original. And our new image, okay, a new figure is called the image. So this one's our new. And I do think a good way to remember this is if I have an original and if I have an image, it's like the picture of it. Okay, so I have an original one and I take a picture of it, that's my new one. Okay, that's my image. So object, original, image is the new one. Translation. So what is a translation? A translation is a transformation in which every point on the figure moves a fixed distance in a given direction. Okay, so another way to think about this is if it's a slide. If I made a shape like this and I slid it around, okay, nothing's changing about this shape. All that's changing, the only thing that changes is where it's at. It doesn't change. It's not rotating, okay, it's not changing its size. All that's happening is it's just moving where it's at. Okay, that is a translation. Okay, this object, okay, has been translated 4 units right and 3 units down. 4 units right, so I took this and I went 1, 2, 3, 4 right and 3 units down, and we have an image. Okay, and a way we can write that is with a translation vector. Now, a translation vector looks like this. Brackets with 2 numbers on top. Notice there's no line in between. It's not a fraction. Okay, it's a vector. Okay, so on top is our horizontal movement. Okay, and if we have a positive, if it's positive, it goes to the right. A negative goes to the left. Okay, so just like on a number line, okay, or just like on a graph, negatives go that way, positives go this way. Well, I bet you can guess what our vertical one then is. If it's down 3, okay, down is negative, and up is positive. Okay, and this is my x change and my y change. Okay, horizontal and vertical. Now we can use Pythagoras' theorem to find the distance an object moves. Okay, so this point has moved to here. Okay, so it's moved that far, this far. This point has moved to here. It's also moved this far, and if I make this with a line, we can see if I take this and I take it to each one, that's the same distance. Okay, and that's because this is a translation. All the points have been moved the same distance. And we can figure out this, okay, with Pythagoras' theorem, and we'll do that here in a second. So translate this object by translation vector -5, 2. Okay, so there's many ways we can do a translation. I think our simplest way is to just pick a point, okay, and then from there, do our vector from there. So this -5 is going to be left 5, and +2 is up 2. So left 5, 1, 2, 3, 4, 5, and up 1, 2. Now this point needs to do the same thing. So 1, 2, 3, 4, 5, up 1, 2. Okay, this point here, 1, 2, 3, 4, 5, up 1, 2. Okay, this point is going 1, 2, 3, 4, 5, up 1, 2. Okay, and you can start to make some, you can start to see where we're going to go. This point is going 1, 2, 3, 4, 5, up 1, 2. Okay, once you've got all of yours, connect the lines. Just make sure you connect the lines correctly. Guys, remember our shape is not changing its shape. Okay, and now we've translated it using this vector. So this is our object. And this is our image. All right, now we need to figure out how far it's moved. To figure out how far something's moved, okay, we need to make a triangle. Okay, so I'm going to pick these 2 points here to compare. Okay, they've moved this distance here. Okay, well, I have a line, but I don't know how to calculate the distance of that line because it's slanted, it's going through here. But I can find this distance and this distance here. Well, this distance we know is 5, and this distance is 2. Okay, and so if we just use our Pythagoras' theorem, a squared plus b squared equals c squared. So it doesn't matter which one's which. We can call it 2 squared plus 5 squared equals c squared. So 4 plus 25 equals c squared. So 29 equals c squared. So square root both sides. C equals square root of 29. And we can approximate that to probably about 5.4-ish. Okay, so our distance is moved 5.4, or exactly square root of 29 units. Okay. Translate the quadrilateral ABCD, 2 units right and 4 units up. Okay, so let's do it. 2 units right, 4 units up. So let's take A, 1, 2, okay, and up 1, 2, 3, 4. Okay, and this is going to be, this is A, we label this one A prime. So this A with this little dot is A prime, not a prime, A prime. Okay, for B, we need to go 2 right, 1, 2, up 1, 2, 3, 4. Okay, and that's called B prime. C, 1, 2, up 1, 2, 3, 4. Guess what? That's called C prime. And D is 1, 2, up 1, 2, 3, 4. And D prime, and we could connect. Okay, and now we have our object and our image. Okay, use a translation vector to describe this. So, translation vector. Okay, how much to the right did we go? We went 2, so positive 2, and we went 4 up. Okay, remember that the x comes first here. Okay, just like in the alphabet or in a coordinate, x on top, x first, and then y. State the vertex coordinates of the image quadrilateral. So, state the vertex coordinates of the image quadrilateral, meaning what are the new ones? So, we have A prime equals, if we assume these are counted by 1, so 1, negative 1, 3, negative 1, 3. B prime is 1, 1. C prime is negative, or is 1, negative 1. And D prime is negative 1, negative 1. All right, there we go. So this is part A, part B, and part C. Is this transformation a translation? Okay, so remember, to be a translation, each point has to have moved the same distance, so we should have the same shape. So if I look at this, if I look at my black triangle and my red triangle, well, which one is going to be my object in my image? Well, this is going to be my image. Why? Well, because it has the primes. So it's a little apostrophe there, you can see. Now if you look here, you might be able to say, hey, those are obviously not the same triangle. Okay, and you might be right, but if we were looking at something like this and something like this, it becomes a little bit harder to see where if they are translations or not. So here's how we can test it. We take each point and we see how far they've moved. And we can do this via distance, so we could do like a distance triangle with Pythagoras, or we could just count. So C is gone, 1, 2, 3, 4. So C has moved for C. Okay, we've gone 4, and we've gone up 1. For B, the vector is 1, 2, 3, up 1. So we've gone 3, up 1. And for A, we've gone 1, 2, 3, up 1. Okay, so we can see A and B have gone using the same vector, but C has not. C's gone a little bit too far to the right. If C had gone here, not so far to the right, we would have the same triangle. But C didn't. And so, is this transformation a translation? No. C is not on the same vector. All right.